Welcome back, everyone, to this lecture on ridge regression. In this lecture, now that we understand theory and intuition behind ridge regression, we're going to move on to implementing L2 regularization, that is, ridge regression, with Python and scikit-learn. Before we head straight to the Jupyter Notebook, however, I want to discuss a few important notes to keep in mind when dealing with scikit-learn. The first important note is that internally within the class call for ridge regression, scikit-learn refers to lambda as alpha within the class call. The main reason for that being is the tunable hyperparameter across many different model types within scikit-learn is just always called alpha. That way you don't need to memorize all these Greek letters referring to specific equations for various models. Instead, they decided to try to maintain a uniform framework as possible where these tunable hyperparameters are just going to be referred to as alpha. So keep that in mind. Later on, when you see me in the Jupyter Notebook editing the alpha parameter, really what it is for ridge regression is that lambda parameter that we discussed earlier. Just a thing to keep in mind. Another important note is later on, we're actually going to perform cross-validation to choose that best parameter value. And what scikit-learn uses is something called a scorer object. Essentially, what are you trying to score by? Root mean squared error, a mean absolute value, etc. The caveat being is that all scorer objects follow the convention that higher return values are better than lower return values. So what does that actually mean? Well, for example, obviously if you're running some sort of test, a higher accuracy is better. But what if you're running a regression task? A higher root mean squared error is actually worse. In order to maintain a uniformity across all models and all tasks, what scikit-learn does is it fixes this by using a negative root mean squared error as its score metric. That means the higher a negative root mean squared error is, the better it actually is. So across any scorer, the higher it is, the better it is. And it fixes that issue for certain error metrics by making them into negative report backs. So the main reason for that, again, is that this allows for uniformity across all scorer metrics, even across different task types, where something like accuracy and classification, higher is better. In the case of regression, they tweak root mean squared error to be negative root mean squared error. That way the convention, higher is better, is retained. And the same idea of uniformity across model classes applies to the idea of referring to the penalty strength parameter as alpha, regardless of the typical notation for that particular model's equation. So something to keep in mind, they're starting to get a very uniform framework for scikit-learn, which comes at a small price of having to think a little bit about what parameters you're actually adjusting and how they relate to theory and intuition that you've already learned about. But in my personal opinion, that's actually a good thing because it requires you to understand the model before you actually just implement it in scikit-learn. Okay, with that all being said, let's actually see how easy it is to perform ridge regression and cross-validation of ridge regression with Python by jumping to the Jupyter Notebook. Okay, here we are at the Jupyter Notebook. Recall in the regularization series of lectures, we had a data setup lecture where we went ahead and created the polynomial features and we performed feature scaling with standard scaler. So that's all set up for us. That way we can jump straight into creating and applying the model. For ridge regression, what we say is from sklearn.linearModel, make sure we spell that right, we're going to import, and the first thing we're going to import is just ridge. And I encourage you to call help on ridge so you can get an idea of what's going on here. But the main idea is everything we discussed. We have our original residual sum of squares, and then the penalty parameter, called alpha in this case, times the squared weight coefficient. In this case, they're calling it W, but for the case of regularization, as we discussed, it's going to be that beta coefficient. So this is the exact minimization objective function that we just talked about. So again, it's linearly squares with the addition of this L2 regularization term and this alpha penalty factor, which was lambda. So now if you see here, we have to tell the ridge regression what alpha to start off with. So let's go ahead and choose an alpha value. Later on, we'll show you how to use cross-validation to choose it. But what we're going to do is we're just going to start off with a ridge model saying ridge, and we'll say alpha in this case is equal to 10. And then this ridge model, we basically run it just like a linear regression model. So after choosing that hyperparameter, we will say ridge model dot fit, and we fit it to xtrain and ytrain, just as we would with a normal linear regression model. After running that, it should report back the model and its parameters. And again, just like a linear regression model, we can call test predictions and assign that to ridge model and predict off the test features, that is xtest. Okay, so everything is pretty much the same as the linear regression. It's just you have to choose the alpha parameter. So you have this tunable hyperparameter to choose. How can we actually get performance results? Well, pretty much the exact same thing. We'll say from scikit-learn.metrics, and then we will import mean absolute error and then mean squared error. So after importing mean absolute error and mean squared error, let's just create some variables here. Mean absolute error is going to be equal to the mean absolute error function, and then we're comparing the y-test values to our test predictions. And we can get a mean absolute error of 0.577. And let's do the same for root mean squared error. So we can kind of see the standard deviation of these results. And that would be NP square root. And then we're going to take the square root of the mean squared error, pass in y-test, and test predictions. And then we get a root mean squared error of 0.89. Okay, so if you ran the data setup with the exact same train test split functionality that we did, that is to say with the exact same random seed, you should get the exact same mean absolute error and root mean squared error value that we did. If you're getting relatively close values, it means you just did a slightly different train test split than us, and that's okay too. Okay, so the main question now is, how do we know alpha is equal to 10 was the best choice? Well, we actually don't really know that. What we need to do is use cross-validation to test a variety of alpha parameters on cross-validated data sets. So how do we actually do this? Well, this is such a common task that scikit-learn actually comes with two versions of the ridge regression model. And we can say from sklearn linear model import, and we can say ridge CV, and that stands for ridge with cross-validation. So what ridge CV does is it's actually going to perform cross-validation for a variety of alpha values here. And then what it's going to do is it's going to report back the best alpha value performance based off this cross-validation. And recall, cross-validation in this case is just going to get the average error metric for all of these. Now, as we mentioned, the score metric we have to provide to ridge CV is going to be slightly different than what we expect, because by scikit-learn's convention, all the score metrics have the result where higher is better. So what do I mean by all this? It means when you're setting up the ridge cross-validation model, and you say ridge CV, if you do Shift-Tab, you'll notice the main difference here is the alpha's parameter. And the alpha's parameter is now a tuple of different alpha values to test out using cross-validation. So instead of just one alpha parameter, you'll provide several, and then it will report back based off your scorer metric and your cross-validation what was the best performing alpha parameter. And as you begin to scroll down, you'll also notice they have this scoring metric, and right now it's none. We'll explain it in just a second. And it has this CV. It also has the ability to store the values for all the cross-validation folds. I would not worry about that, so keep that as false. But this CV parameter, if you scroll down here and start reading more about it, obviously alphas is the list of alpha values to try, which is the regularization strength parameter. If you continue scrolling down till you get to that description of CV, this is just the integer, and it's the integer of how many folds you're going to do in the cross-validation. So if you leave it to none, it's going to use the efficient leave one out cross-validation. Keep in mind, if you have a huge data set, that could take a lot of time. So instead, what you may want to do is actually recall something like CV equals 10 or something like that. So this is essentially the CV k number of folds. For our use case, this data set's actually small enough that it's not too bad to just do leave one out cross-validation. So we'll go ahead and just do the default value. The main thing we'll specify here are the alpha parameters to choose, these alphas, And in fact, these default values are looking pretty good. So let's just try this. I'm going to copy this so we can see it. But again, I'm not going to change any defaults here. I'm just showing them for visualization purposes that we can display what we're actually doing. So I'm going to do cross-validation 3 separate times with 0.1, 1.0, and then 10. And I would encourage you to recall the cross-validation discussion that we had, where I also mentioned we have a holdout test set. So essentially what we're doing here with 𝒕𝒕𝒉𝒐𝒏, because I'm only going to fit it to xtrain, that makes 𝒕est kind of a holdout test set. And I'll show you why, because I'm going to create this 𝒕𝒕𝒉𝒐𝒏 model. We'll say 𝒕𝒕𝒉𝒐𝒏 model, and then what I'm going to do is I'm going to fit it on xtrain and ytrain, which means I'm only using the training set for the purposes of hyperparameter tuning. So in reality, this training set, if I'm using of 𝒕𝒕𝒉𝒐𝒏, it technically becomes more than just a training set. It's going to become the training set, plus a small portion of it is going to stay as a validation set in order to check the performance of these 3 alpha parameters across however many folds you're doing. So this is pretty much the exact situation we described in the cross-validation lecture when you saw us hold that purple block out as a kind of holdout set. So what's actually happening here is you can think of xtrain as that whole data set minus the holdout, and then we're going to do a bunch of folds and get the metrics on the validation sets. So go ahead and run this, and you'll notice the larger the data set, the longer this is going to take. This data set's quite small, so we're okay here. And then it tells you the different alphas it provided. So which alpha performed the best? It's actually going to tell you, just say 𝒕𝒉𝒐𝒏 model, and then call alpha underscore, and it reports back the alpha that performed the best. In this case, it was 0.1. So then the question arises is, what was it actually using to measure the best performing alpha? And in that case, you would have to have provided a scoring metric. How can we choose what scoring metrics are available? Well, in that case, you can say from scikit-learn.metrics import, and then in all caps, you're going to say scores. After importing that, this is actually a dictionary, and you can say scores keys. It's actually kind of a dictionary-like object. And you'll notice it brings back this list of keys, and these are all the different types of errors you can try to work with as your scoring metric. And again, keep in mind that every single one of these error metrics, it's transformed so that higher is better. So we can see here, instead of saying mean absolute error, we're saying negative mean absolute error. Because for normal mean absolute error, the higher, the worse. You don't want a very large error. However, if you were to assign a negative mean absolute error, that means higher is better. And obviously, not all of these metrics or scoring metrics are going to be relevant for a regression task. So you can't just use any of these, like recall, accuracy, and precision. Those are for classification metrics that we'll talk about later on. But we are already familiar with things like negative mean squared error and negative mean absolute error. So let's provide this string as the error metric we're trying to optimize for. So I'm going to copy this. I'm going to come back up here, and now I'm going to say for scoring, use, and then I'm going to paste in that string. So what's a little annoying about this scoring metric is you have to actually either memorize this string, or you have to import metrics scores and then look it up here. So just keep that in mind, that you can't just pass in something like MAE. You have to memorize this whole string or look it up. So now we're going to run this again, and you should pretty much get the same result if you run this again, but it's just clarifying the scoring metric being used to choose the best alpha. So we run that, run this again, it reports back, hey, I'm checking these 3 alpha values, and I'm scoring them based off negative mean absolute error. And then if you check out the alpha it found here, still it found 0.1 as the best performing alpha out of these 3 options. And obviously, if you want, you can keep honing in on alpha, and maybe you can say alpha is equal to 0. Maybe no regularization actually makes sense here. Or you can try something like 0.2 or 0.5, etc. So you can start moving away from 0.1 if you want to hone in on the absolute best alpha. But let's go ahead and just check performance based off this alpha parameter. So we're going to comment this out, and let's go ahead and comment that line out and calculate the metrics again. To do this, I'm going to copy and paste some code up here. So we'll say, copy and paste this, test predictions, except instead of ridge model, we'll say ridge CV model. Run that, and now let's run the exact same things we got before. So we'll say MAE is equal to mean absolute error, y test, and then test predictions. And let's grab root mean squared error, and that's actually equal to the exact same thing we wrote earlier, so we can just copy and paste this. Since I'm calling test predictions again. And let's check out the improved results, hopefully. So we have mean absolute error and root mean squared error. So now, with an alpha value of 0.1, which was found to be the best alpha value according to cross-validation on that training set, if we look at the test set, which is kind of a holdout test set in this case, since I'm not actually tuning based off this test result, I have a mean absolute error of 0.42. If we compare this to the alpha value of 10, that had a mean absolute error of 0.57 on the test set. So I did find a better alpha value with cross-validation using ridge CV. And just like our previous linear regression model, what I can always do is come back to my ridge CV model, and I can grab the coefficients directly and view them here. Notice that for L2 regularization, none of these coefficients are 0, or actually none of these coefficients are even that close to 0. That's going to be different later on when we take a look at lasso regression, which can actually squeeze coefficients all the way down to 0. Okay, and as a last note, you can check out Ridge CV Model tab to take a look at all the values here. It has a lot of information about the internal scoring, like how it did on certain cross-validation scores, or what was the best score during its testing, and it returns back the highest negative mean absolute error it got. Whether or not that's super useful, I don't know, but we can see here that overall the average mean absolute error here on the Y test set happens to be 0.42, which is really the metrics you should be looking at. Its performance on new unseen data. Okay. So that's it for ridge regression. Hopefully you saw it was pretty cool and easy to use, especially considering that you don't even really need to do any setup for ridge cross-validation. You just import it, choose your alphas, choose your scoring metric, and let it do its work. Okay, I'll see you at the next lecture where we're going to discuss the theory and intuition behind lasso regression. I'll see you there.